Hey guys, sorry I'm not there today. I've been sick all winter break and it's taking everything I got just to make this video for you guys. So I hope you can hear and clearly hear me, and we'll try to make this as painless as possible. We still need to keep moving forward because we're limited on time. And I want to go fly kites and go to the fire station next week. And hopefully I'll be back to normal by then. Anyway, we're going to start looking at trig functions, okay? But just to start us off, why don't you list all the facts you know about triangles? And I know you got your headphones in at this moment, and but just think about angles, sides, types of triangles, etc. All right, these should be like most common things you thought of: equilateral right, isosceles obtuse, scalene acute. These are all types of triangles. Characteristics: well, they have three sides, three angles. Longest side and largest angle are across from each other, and shortest side and smallest angle are across from each other. No brainers. Again, we're looking at SRT6. We're going to understand that similarity and side ratios in right triangles are properties of the angles in the triangle, leading to definitions of trigonometric ratios. Again, we had this idea last week about similar polygons or similar triangles, same shape, different size. All right, so right triangle trigonometry is as old as it can be. Uh, trigonon and metria, triangle measurement, from Greek words. The Greek mathematician Hipparchus, Nicaea, and Ptolemy used the special relationship of trigonometry more than 2,000 years ago, primarily to study astronomy. Hence, thanks to these guys, they were the first people to discover how far the moon was from us, and in relation, how far the sun was away from the earth. So that's pretty amazing, the fact that they could come up with this with just paper and pencil by just using these properties we're going to get into with this unit and the next one. So, given the triangle to the right, we have to learn to identify sides of relation to a particular acute angle. Guys, this is the hard part. If you can get past this with these labels, all of it should be downhill. Okay? So, what does it mean to be acute? We all know less than 90 degrees. Which are the acute angles? Well, it's going to be x and y. Okay? The side opposite of the right angle is always you know this, oh, hypotenuse. Okay? They'll never change. It's always across from the right angle. Other sides to think about: opposite. If x is the acute angle, I like to say the reference angle, the leg opposite of x would be known as the opposite leg. So if we're focusing on this x, opposite of that would be the opposite leg. It's pretty much straightforward, but a lot of students have problems with this. But hey, it's fine. You're learning. Label it. As you know, I'm probably going to use height for this one and OPP for opposite. That only leaves one more side to go, which is the adjacent leg. Okay, as you know, the adjacent means next to. Our classroom is adjacent to Mr. Christopher's room. Well, what I would write here, we're in Mr. Christopher's room. Miss Lloyd's room is adjacent to my room because it's right next to it. Or as I call her, Miss Lloyd. Oh boy. Anyway, going back to what I said, I'm going to use abbreviations OPP, hype, and adjacent, or ADJ, to label these things. Labeling is important because that's how these trig ratios fit in because of these labels. If y was our acute reference angle, where would the hypotenuse be? Take a second. All right. Hypotenuse should be up here. Again, opposite of the right angle. If this is our reference angle, opposite to it, let me erase those so we can see. Opposite across the triangle would be the opposite leg. Well, the leg right next to the angle would be adjacent. You've got to get these labels down in order to get this trig stuff, okay? Again, we were right, naturally. I'm going to label the lengths of this sides of this triangle with A, B, C, D. I said D. There's only 3 sides. There are 3 basic trigonometric ratios that can be used with any right triangle. Guys, go ahead and copy this. You can go to the next blank page in your composition book. I suggest you copy this triangle. You will use it for the next 3 slides, okay? The first one we're going to talk about is sine, or sin, as some students call it. Sine ratio is equal to the opposite leg over the hypotenuse. Either acute angle can be used as a reference angle. So, this is the function, sine theta equals opposite over hypotenuse. If I was referencing the x, it would be A over C. If I was referencing the y, it would be B over C. And you have to see that in order to get this. Again, if I was at the x, opposite would be A over hypotenuse. If I was referencing the y, B would be opposite over C. So go ahead and jot this down. Then we're going to move on to the next one. Pause it if you need to. The next one will be cosine, or cosin, as some students call it. Ratio is equal to the adjacent leg over the hypotenuse. Either acute angle can be used as a reference angle. Again, this is the function. It will be on the formula sheet. Notice it's adjacent over hypotenuse. Hence, if we're referencing the x, it would be B over C. If we're referencing the y, it would be A over C. See how these sides can take on different labels based on your reference? You've got to get that down. Hence, it helps when you label these things. You'll see when we get to an example. And last would be tangent. As you know, I think we use this for tangent lines that, well, never mind. We haven't done that unit yet. We're going to do that in circles. Anyway, the tangent ratio is equal to the opposite leg over the adjacent leg. Either acute angle can be used as a reference angle. And again, this is going to be on the formula sheet. But again, copy this down in your composition book. Opposite over adjacent. So if I was referencing x, it would be A over B, opposite over adjacent. And if I was referencing y, it would be B over A. Again, referencing y, opposite, excuse me, over adjacent. Okay? Again, that's in reference to y. Get used to making these labels, so it'll make your life easier. Alright. There's also a nice little trick that I learned when I was in school. You can remember these formulas by remembering chief, so, ga, to, wa. Well, that came out weird. Chief Sokotoa. Some students call it Chief Sokoto. Whichever way you want to memorize it, but S obviously stands for sine, OH for opposite over hypotenuse, Ka would be cosine over adjacent and hypotenuse, and tangent, opposite over adjacent. That's going to take everything I got, guys, to get through this lesson. For those of you who like graphic organizers and you may want to make a foldable, you can go ahead and go get a colored paper over there from the shelf. And this is optional. You don't have to do it. But if you're one of those types that like these kind of things, then go ahead. Just pause the tape, get your paper, and you're going to want to fold it hot dog style. Ideally, this top part's going to fold down over this bottom part. Notice where you got to cut it to make little doors. You're going to fold along this line. And you're going to want to draw lines here so you can separate your boxes. Next. Again, this is referencing you're only cutting one side, okay? This is when it's flipped over. Now, this is folded down, so you're looking at the doors. Go ahead and write sine, cosine, and tangent on it. Again, you're cutting that one piece of, that one-sided, sorry, the flap pretty much is the only thing you're cutting. Don't cut all the way through. Then on the inside, you open it up, copy this triangles on all of the inside of the doors. Remember, this is where it's folded. These are the only ones you're cutting halfway. Copy these triangles. Sine in reference to x would be opposite over hypotenuse. So A over C. Cosine x would be B over C, adjacent over hypotenuse. And tangent would be opposite over adjacent. So A over B. Again, labeling helps. If you want, you can go ahead and put OPP here and height. Notice I'm only labeling these two because that's the only thing sine can be used for. Bottom would be adjacent over hypotenuse, and opposite over adjacent. Again, this is all referencing x. So if you want, go ahead and make this foldable. If you don't want it, so be it. Excuse me. Alright, let's practice some now. This paper should be over there on the table, hopefully. Miss Lloyd is there. She can help you out. Because all of this was kind of last minute, guys. Anyway, all you have to do is find the sine, cosine, and tangent. I'm only going to do one of these because I got the answer key and I'm going to post that. Okay, but if it doesn't work, ask Miss Lloyd to print off a copy for y'all to share. Alright, we're referencing angle A. Since I'm referencing A, I'm going to label 53 hypotenuse. Opposite of A would be this side. That's the opposite leg. This 28 is next to the A, so it's going to be adjacent. Guys, this is the very first step you need to do. Next, as you know, sine A is going to be opposite over hypotenuse. So 45 over 53. You would normally reduce this, but I don't think this reduces at all. Yeah, I don't think it does. Next is cosine. Remember, that's adjacent over hypotenuse. Adjacent's 28 over hypotenuse. And see how this makes it easier with the labels? Tangent A, again, is opposite over hypotenuse. And that's 45 over 28. And again, if you have your calculator, reduce this if you can. Let me think. 4 and 7. Yeah, I don't think this reduces either. Go ahead and do that for all of them. And check the answer key I posted. Let me check my time real quick. Alright, let's keep going. I'm just going to chase some ideas about similar triangles. If you write the ratio in a fraction form for sine x for each of these triangles, what do you notice? Go ahead and take a minute. Sorry, I'm using my laptop so you can't see the whole screen right now. This little one and this big one. Okay. You'll notice the little one is A over C. That big one is 5A over 5C. But as you remember, these 5's are going to cancel. It reduces down to just A over C. The same thing. These triangles are going to be similar because they have the same trig ratio. Okay? We're going to look at characteristics. I think we said this last week as well. Similar triangles, again, you may want to write this down. Similar triangles, same shape, different size. We'll say that for the rest of the class. But again, you'll look at these triangles. It's only been scaled up about 5. These are going to have the same ratios as discussed previously. When you're dealing with similar triangles or similar polygons, corresponding angles have the same measure, meaning this x, if it was 15, then this x is going to be 15. And in hindsight, since that's 15, and again, I just made this up. Let me see, 15. Subtracting it from 90, because remember they all add up to 180. 90 is already used up, so I'm going straight to 90. I probably could have done this in my head, but, you know, I'm not feeling that well. 75, A, 90, yep, that works. Which means this is 75, and this has to be 75. Okay? Another concept, the ratios of the corresponding sides are proportion. We proved that on a couple slides ago. If we were to stack these sides up, they would equal the same. These triangles are similar, so find the trig functions for these. So, sine x, again, opposite. This would be adjacent. This would be hypotenuse. So I'm just going to go straight for the numbers. 3 over 5. Cosine x is going to be 4 over 5. And tangent x is going to be 3 over 4. Over here, sine y, again, opposite, adjacent. This is 10, hypotenuse. This is going to be 6 over 10. That reduces to 3 over 5. Cosine y, 8 over 10. That reduces to 4 over 5. And then tangent y, I'm going to write it down here. Is going to be 6 over 8, but that reduces to 3 over 4. The fact that these trig ratios are the same means x and y are the same angle. These triangles are similar. Okay? Let's try another one. Well, thought there was another one. So, as far as proving these triangles are similar, we use the trig ratios to discover that. Well, there's a question here. What must be true about? We just said that. Measure of the angles are congruent. Let's move on. Our triangles have a pair of congruent acute angles will always be similar. Use your calculator to find sine 42. Guys, go ahead and get in the habit of getting your calculator. It needs to be in degrees. I think all the Casios are already in degrees, so you don't have to worry about it. All you have to do is hit the sign button. You'll find it. Just look for it. Then it'll pop up on the screen, sign, parentheses, and then plug in the 42, close parentheses, and then hit equal. And you're going to get this rounded-about answer. Of course, yours will be longer than that, but I rounded mine. Is this true for both triangles? Of course they are, because we just discussed that these triangles are similar. Even if it's scaled up by 5. We already had this idea. Now let's see if these triangles are similar. So again, sine x. This time I'm not going to label it, but I know it's going to be opposite, so that's 5 over 13. Cosine x. That's right, 12 over 13. And then tangent x. Five over 12. Over here, sine y, 8.7 over 20. cosine y would be 18 over 20. And this reduces to, let's see, divide that by 2 to get 9 over 10. And then tangent y would be 8.7 over 18. So, just looking at this cosine y and this cosine x, these triangles are not similar. They don't have the same ratios. Okay? If triangles have trig functions that are equal, then the triangles are similar. We just discovered that. If triangles are similar, then the trig function of corresponding angles will always be equal. Okay? It doesn't matter how tiny the triangle is or how big the triangle is. And when I mean big, I'm talking in reference to Earth, the sun, the moon, or even bigger than that, our galaxy to a neighboring galaxy who happens to be spinning the same direction to some black hole. If you can make a 90 degrees out of it, you can get this relationship. What trig functions do those ratios represent? BC relative to x. That'd be adjacent over hypotenuse, so that probably means cosine. What else can you say? Oh, EF. I think EF is the same. Yeah. What else can you say about these triangles? They're probably similar. Cosine x and cosine z, we just talked about it. They're similar because x and z have the same trig ratios, so they're going to be the same. It's just another idea to show similarity. What's true about these triangles? Now, being that 32 is up here, well, wouldn't 58 be up here? And if 58 is in this taller one, wouldn't 32 be down here? Guys, these triangles are similar too. They are similar triangles, they are equal. Okay? Remember, interior angles of a triangle add up to 180. Which trig functions fit? So I do AB. Relative to 32, AB would be opposite over adjacent, so that's probably tangent. 58 for ED, 58, ED, opposite over adjacent again, so that's tangent. 32, let's back up here for AC. It's opposite over hypotenuse, so sine. And 58 DF, adjacent over hypotenuse, so cosine. Find the sine, cosine, tangent of A. Then describe how they are related. So go ahead and take some practice. I think my answer's on the next slide. Just go ahead and pause the video. Alright. Well, never mind. I thought it was. But I also think this video is long enough. Go ahead and try this out if you want. Compare answers at your table in a respectful manner, because I think I'm all out of gas. There's the answers for that one. So if you want, you can do this one. Same idea. Find sine, cosine, tangent of A. Pause the video so you can copy these triangles on the table. Describe how they're related. And then you can look at the answers here. Based on these results, you could say they're similar. Alright, this goes into complementary angles. I'm going to do that tomorrow. You'll work hard on this. Let's see y'all hopefully Friday.